Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. But it's not just another Tuesday live stream. We're continuing a CPU summer where we go through a variety of practical topics to help you work with the new modular controllers from Horner, specifically the new CPU250. So let's take a look at today's topic. Using the micro CPU250 with variable frequency drives. Now, variable frequency drives are everywhere. They're one of the most very common components in the industrial landscape, just about as common as PLCs. So it's important for you to know how to integrate those very common components with the new CPU250. So without further delay, let's get right to it. We're going to start with a quick review of the CPU250. We won't spend too much time on that. We've been covering it pretty heavily this month, as you know. And then we'll dive into variable frequency drives. We'll talk about interfacing with those drives through I/O signals and through networks like Modbus RTU. And there'll be plenty of demonstrations throughout. Here we go. The new CPU250 is one of our new modular controllers that are part of the Micro series that are great for simple and smart applications. Actually, they can do a lot more than just simple applications. But to date, the Micro series has consisted strictly of all-in-one controllers, or controllers that include a display. The CPU200 and CPU250, shown on the screen at the right, those do not include a display. And today we're going to be talking about the CPU250. Okay, the CPU250 is fully featured. It's got all kinds of interfaces on it. I'm not going to spend too much time here, but I want you to see that it's got a full array of I/O type connections internally built in. It's got lots of connectivity like Ethernet and CAN and serial ports. It has the ability not only to have built-in I/O, but also to add modular I/O to the side of the unit using standard OCS I/O modules snapped onto the side. And from a field bus standpoint and industrial Ethernet standpoint, it's got tons of connectivity. Now on the connectivity side today, we're going to be talking about Modbus RTU, which is a great protocol to use for VFD control. So a little preview for you there. Now let's dive a little more deeply into the built-in I/O for the CPU250. Now, one of the highlights of the CPU250 from an I/O standpoint is the fact that it has 34 built-in I/O points. That means it can take care of a lot of applications. And one of the highlights are the flexible inputs, which are 8 inputs that can be either digital or analog. So if you have a very heavy analog application, you have plenty of analog inputs. If you have a heavy digital application, you've got plenty of digital input. So lots of flexibility in the built-in I/O of the CPU250. And today we're going to highlight the I/O signals that allow us to do VFD control using I/O. Another preview for you there. All right, now we're going to dive into variable frequency drives. What is a variable frequency drive? Well, it's an intelligent electronic component that's designed to control an AC motor. Okay? VFDs change the frequency and the voltage of the AC that they send to the motor, which allows the VFD to control the motor speed. Now, how does a VFD work? Well, it converts the AC that's connected to it to DC, and then back again to a variable frequency AC that it sends to the motor. And as I mentioned in the open, VFDs are everywhere, just like PLCs. Let's start by talking about how VFDs and PLCs are used together. First of all, there's no requirement that you have to use a PLC to control a VFD. They can definitely work standalone, and they're often used that way. However, it's very common for drives to be controlled by PLCs, so you get good coordinated machine control. And the most common method of controlling a VFD from a PLC, there's two of them actually. First would be to use I/O signals to start and stop the motor, control the speed, etc. Okay, those are digital and analog signals that every PLC includes. All right, but that's just one method. Another method is to use a network and send those same commands digitally instead of through an I/O signal. Now let's start looking at the common control connections if you're going to use I/O from a PLC to control a drive. Now there's lots of different I/O that could be used, but this is probably a basic common type approach. First of all, from the PLC, you're going to have a digital signal that is a run-stop command to start and stop the motor. All right. There'll probably be a forward-reverse command in a lot of applications. All right. And there'll definitely be a speed reference of some sort. And usually it's an analog output from the PLC to the drive that's scaled to frequency. So a minimum analog signal to the drive from the PLC will give you a minimum frequency for the motor, and a maximum analog signal will give you a maximum frequency for the motor. All right, so that's the signals that are most typically going from the PLC to the drive. Now, coming back the other direction, you're going to have a digital signal that tells you run status. Okay, so the PLC knows if the motor's turning or not, and there'll be some sort of feedback, usually another analog signal coming into the PLC this time that is scaled for frequency. So the PLC knows the frequency that the drive is running at that tells them the speed of the motor. Okay, so again, there's lots of different variations, but this is the most common setup. All right, now what if we're talking about using network connections between a PLC and a drive instead? Well, there are so many choices available. You've got Modbus, both serial as well as Ethernet. You've got Profinet and Ethernet IP, which are everywhere. You've got CAN Open, and there's many more than this, okay? I've only mentioned a few of the most common, all right? And even though all these networks are available in most drives, okay, usually it's Modbus RTU, or Modbus over RS-485, is the one that's the most commonly available built into the drive as standard, okay? Usually those other protocols are options that have to be added to the drive or that cost more, frankly, whereas usually Modbus RTU is built in. All right, now let's talk specifically about the CPU250 and its interfaces that it supports for controlling a drive. From a network standpoint, it supports Modbus, both RTU and Modbus TCP, Modbus over Ethernet, and it supports CAN Open. So both of those are options that are built into the CPU250 if you want to control using a network. If you want to control using digital and analog I/O, well, we mentioned earlier, the CPU250 has a huge amount of built-in I/O and can easily control a drive that way. Okay, so you've definitely got options. Now, which should you choose? Should you use the I/O approach or should you use the network approach? Since you have choices, I know a lot of folks, when they get choices, they get worried about making the wrong choice. Well, let's talk about the advantages of each. Okay, let's start with I/O. What are the advantages of using I/O to control a VFD? Well, it works with any drive. All drives are going to have the ability to be controlled via I/O signals. Okay, why is that important? Well, I've had customers tell me that the advantage of using I/O is that if they ever have to swap out the drive and they can't get an exact match for the drive that was originally put in the system, they have a lot of choices of drive replacement. In other words, they can put pretty much any drive in there and control it using the I/O, and they don't have a reprogramming or anything else that they're going to have to do. Okay, so those are the advantages of using I/O. But networks have an advantage as well. First of all, if you're not using I/O signals to control the drive, you can use those I/O signals for other purposes to control other components. So that's an advantage. That can save cost in a lot of cases. And when you're connected over a network, you have the option of receiving detailed diagnostics from the drive. So not only that the drive is faulted, but what the fault codes are, for instance. So that's extra information that can be really valuable. So which should you choose? First of all, there are no wrong answers. Both approaches are valid, and you can choose either approach. Now, for today's demo, we're going to use both. Okay, we're going to use I/O signals to control the drive in our demonstration today, and we're going to use Modbus RTU as diagnostics or for diagnostic purposes. So this gives us the best of both worlds. All right, we have the advantages of the diagnostics from a Modbus standpoint, and we have the advantage of being easily able to swap out a drive in a pinch by using the I/O signals instead. Okay, so we're going to use both of them and get the best of both worlds. All right, so let's start with the specifics on what we need to do with the Modbus connection. Well, first of all, Modbus RTU is pretty uniform. It's a twisted pair plus additional conductor that's needed for RS-485 communications. All right, so the twisted pair is going to carry the communications data, and then the extra conductor is going to carry common to avoid any kind of common mode ground issues between the two components. So all three wires are important. The communication signal needs to be over the twisted pair, and the extra conductor is where you would put the common. And that extra conductor can be half of an otherwise unused twisted pair. Okay, now termination needs to be done at both ends of the physical network, or both physical ends of the network. On the drive side, many drives have a switch you can throw or some other method of adding termination on that end. In the case of my example here with the Control Techniques drive, I physically added a 120 ohm resistor to the end of the network. Now on the CPU250 side, all right, I could have added a physical resistor on the end of the network, but that can be difficult using modular jacks sometimes. Luckily, the CPU250 does have a way of adding termination simply by turning on a system bit. So there on the screen, I'm showing you that SR152.1, when turned on, will add termination to the MJ2 port, which is the RS45 port. So that can be easily done in your logic. Now from a Modbus reference standpoint or Modbus address standpoint, since we are using Modbus strictly for diagnostics in my example today, I have chosen a series of Modbus addresses in the M400 drive that allow me to monitor voltage and power, RPM, a signal that tells me if the drive is healthy or not, and if it's not, I have the ability of reading trip codes. Not only what the trip codes were, but when they occurred. So that's the specific diagnostics I'm going to be using today in our demonstration. You could choose completely different references, and if you're using other drives, of course, you're going to have different Modbus addresses. All right, now let's talk about the I/O connection between the two devices. All right, so first of all, there's a digital output that I've wired in my demo to Q1 on the CPU250 that's going to tell the drive to run, okay? Then the drive is going to feed back a signal into input 1 on my demo for the CPU250 that tells the CPU250 that the motor is at rest. So if that signal's on, you know the motor is at rest. All right. Then I've got an analog output going from the CPU250 to the drive. That is the speed reference. Okay. It's a 0 to 10 volt signal in this case, and it's scaled to frequency or motor speed. Okay, so at the minimum analog value of 0 volts, I'm going to get the minimum frequency out of the drive. At the maximum analog voltage of 10 volts, the drive is going to cause the motor to turn at maximum frequency. So that's the speed reference from the CPU250 to the drive. And then we have feedback coming back the other direction, another 0 to 10 volt analog signal scaled to frequency, so the CPU250 knows the speed that the motor is turning at. It's a verification. And then we also have 24 volt and 0 volt connections between the two components. And again, for specifically the Control Techniques drive that I used in the demonstration, I've got the terminal numbers listed there as well. Now, in the upper right-hand corner, I'm showing the addresses that the specific I/O points are mapped to in my demo program, okay? And you'll notice that everything is pretty straightforward. But the V1 terminal, which is the first analog output, that's voltage analog output, that's mapped to AQ5, okay? And then the first flexible input, which is terminal I9, when it's configured as an analog, that is mapped to %AI1. Okay, so just to make clear what the I/O references are, I'm showing them there on the screen. Okay, now if you need more details, especially on the Modbus side of things, okay, for interfacing with this drive or just drives in general, I've got a good video that we did just a month ago that you can use that has more details than I'm giving you today. And there's a link there on the screen. You can easily find it on our website or by just doing a Google search and finding it on YouTube. All right, so here we go. Let's go ahead and move to the demonstration portion of our topic. For a demonstration, let's go ahead and start on the bench. Okay, so let's take a look at what we've got here. All right, so we've got our CPU250. All right, and to the left over here is where I have my motor and drive mounted. Quite sizable. They don't really fit in frame. You can just barely see the motor over there. To make things easier, on the right here, I've got, my awesome editor, Emily, has put a view of the variable frequency drives, keypad, and display, so we can see what's happening and follow along. Okay, so I've chosen to do a hybrid approach with this demonstration of interfacing the CPU250 to the drive. So with a hybrid approach, we use both I/O points to interface to the drive as well as Modbus. Why do we do this? Well, we get the best of both worlds. So we have the ability to really control any drive through I/O, one analog in, one analog out, one digital in, one digital out. And we get the benefit of the diagnostics over Modbus. So if we ever have to quickly swap out the drive, we can do so. And we can basically swap it out with any drive that we can control via I/O, which is almost every one of them. And we also get the benefit, while we have our original drive or any replacement drive of the same type, that we can very easily get lots of diagnostic information over Modbus. So again, best of both worlds. That's what we've got here with this hybrid situation. All right, so in terms of what we've got wired, we have one analog output here, which is basically providing the speed reference for the drive. Okay, we have an analog input that's wired here through one of the flexible inputs. That is providing feedback on actual speed for the drive. And then we have a single output going to the drive as a run signal and a single input coming back, basically telling us that the drive is at rest, okay, that we're not moving. That's how that signal is set up. The drive is not moving. Okay, and then we've also got common and 24 volt connected as well here. And of course, here is our 24 volts. Here is our RJ45 for talking Modbus RTU. All right, so let's now turn our attention to Cscape and see what we have going on here. All right, so let's get started through the hardware configuration. And because we're primarily controlling this system using I/O, let's take a look at our local I/O. Now, there's absolutely nothing special going on the single digital input and output that we're using here with the drive. These are all just default, so I'm not going to bother to go through that yet, or at all, really. And then we just have one analog input, which is configured as a flexible input, and one analog out. So let's take a quick look at these. Now, for this particular drive, I've chosen to use 0 to 10 volts. All right, so I'm using the first flexible input. In my case, I could use any of them. And I have it set up for 0 to 10 volts on the input side, as well as 0 to 32,000 on the range. So at 10 volts, we're going to have 32,000 counts. At 0 volts, we're going to have 0 counts. And as I mentioned before, this is providing the feedback from the drive telling us the speed that the motor is turning at. Okay, so that's the one analog input. The rest of them I could configure however else I needed in my system. On the analog output side, remember, these are not fully configurable. So if I'm going to use voltage, I have to use one of the second group of 4 analog outputs. So I'm going to use the first of the voltage analog outputs, which happens to be analog output number 5, connected to the V1 terminal. Okay, and again, scaling is the same, 0 to 10 volts, 0 to 32,000. And this is providing the speed reference. So when I'm sending 10 volts to the drive, I've done that by stuffing 32,000 in the register, which is AQ5, and that should cause maximum speed for the drive. Okay, so that's what I've got going in the I/O configuration, and again, just defaults for digital input and digital output. All right, so that's all we have going on there from the standpoint of I/O. Now, I don't have a lot of logic in here for controlling those 4 I/O points or monitoring those 4 I/O points. You can add those yourself with your particular application. It's not a big deal. The one thing I did put in here is I do have a default for the variable frequency reference value on power up that I'm moving in there, a value of 32,000 by default. You could do something completely different in your application or make this variable retentive if you want to. The last thing I'll show you in regards to the I/O is the mapping that I've done here. So let's go to our global variable area here. And I've got these 4, I've created 4 variables that are tied to the analog output, analog input, digital output, and digital input. So respectively, we have our frequency reference, our frequency feedback, our run signal, and our motor at rest feedback. And I put a little HW on these to note the fact that these are hardwired. Okay, just happened to do that. That was a choice that I made. All right, so that's pretty much it from the I/O standpoint, and we'll exercise this guy here in a little bit. Before we do that, though, let's take a look, because this is a setup where we're also using Modbus, at least for diagnostic purposes. Let's go in and take a look at our Modbus configuration. All right, so back to hardware configuration. Modbus RTU is a serial port protocol, so we go to the serial port configuration. MJ2 is our RS-485 port. We've selected Modbus Master here, and then we have our 3 levels of configuration. So I'll quickly go through that. I left everything at defaults except I matched the serial parameters to the defaults of the drive. So these are the default drive's serial parameters. The other thing I've done is I've reduced my timeout to ½ a second because this drive is the only thing I have connected to my port. No sense having a long timeout there. Same thing with reacquire time. Okay, I've left polling of the data as fast as possible, and I've taken advantage of the 4 double words of Modbus RTU master status to make sure I have plenty of good troubleshooting information. All right, so there we go with our first level of configuration. On the device level of things, I have a single drive connected, which I've given a convenient name. It's Modbus address number 1. It uses PLC 5-digit addressing, and I took advantage of the additional 2 words of status. That'll tell me if there's a problem with any of the data that I'm trying to retrieve. Okay, so there's not much going on there. It's all pretty much the defaults except for status and that sort of thing. Okay, and then finally we have our scan list. This is the data we're retrieving from the drive. Now in this case, I'm using the Modbus connection strictly for diagnostics, so I'm just doing read commands. If I was doing full control, I would have both read commands and write commands. So let's take a look at the data that I'm looking at here. All right, so I've got 3 words of status information that I'm reading into an array variable of a word type. Okay, just polled read. So I'm reading this data all the time. This is going to give me information including RPM and motor voltage and that sort of thing. Okay. The next thing I'm going to be reading all the time is a single word that tells me the health of the drive. So if there's a problem with the drive, health-wise, I'm going to know that pretty much right away because I'm continuously polling this data. Okay. And then I have a couple of other entries that are not continuously polled, but are only polled when I need them. So I trigger them with another variable in ladder. So the first one that I'm doing that with is the trip history. So if we have a trip, in other words, if that health bit I just looked at goes off, that health word that has a bit within it, if that goes to 0, that means my drive is no longer healthy and I've got a trip condition. So let's trigger a read of the trip history. There's 10 consecutive Modbus words that contain the last 10 trip codes. So let's go ahead and read that information. All right, there we go. That's useful. And then the final bit of data here that I'm reading is similar trip times. So this isn't the trip codes. These are the date and the time of each of the last 10 trips. Also, again, triggered by turning a bit on in my program. Okay, so that's really all there is to the Modbus configuration for this particular example. All right, let's take a quick look at our ladder logic. We've already taken a look here at this default frequency value that we're gonna make available here. Let's go to our Modbus RTU bit of code that we've got here. All I've really done is I've broken out the 3 words of data that I'm retrieving from the drive, that's status information, into individual variables: voltage, kilowatts, and RPM. Okay, you could use whichever ones you want. This is just an example. All right, and then if I've got a trip that occurs, in other words, if I detect that my health bit is no longer, or health word I should say, is no longer a 1, then I'm going to turn on a 1-shot, which is going to cause me to retrieve those 2 words of Modbus, or more than 2 words, those 2 entries in my Modbus scan list. Okay, and then just like every Modbus example I do for Modbus RTU or Modbus TCP, I create a Modbus OK bit. Okay, basically by determining that the number of good messages is incrementing, which means I'm successfully talking to the drive. So this is the same logic I've used before, and it's well documented. All right, so that's what's going on the logic and configuration side. All right, now, of course, because this is the CPU250 and it doesn't have a built-in screen, we're going to go ahead and use the data watch for my little demonstration here. So the first 4 entries of my data watch, those are the analog output, digital output, analog input, and digital input that are wired to the drive, so we can see the status of those. And this is my 3 words of status information over Modbus that I'm retrieving. Okay, so let's go ahead and turn on the drive and see what's going on here. All right, so I've got it set for max frequency. Let's turn on the run bit and see what happens. Okay, as you can see, we're ramping up nicely there. And now we're at full speed. And while it's running, I do have the ability to change the speed. Of course, I'm doing it from the data watch. You would likely do it in ladder logic, of course, where you're manipulating the speed based on maybe a PID loop, maybe just some simple logic, whatever the case may be. You're going to be doing it in logic. I'm doing it here from the data watch. Okay, and let's go ahead and move it back to full speed. Okay, and as we do that, you can see this diagnostic information we get. We've got 230 volts, 5 kilowatts, 1800 RPM. Okay, so that information is all happening. Here is the speed feedback, which is, nearing 32,000 hertz. So it's definitely indicating a high speed here, pretty close to max. It's actually at maximum. But remember, we're dealing with analog here, so it's not going to be exact. Okay, and of course, we can turn the drive off by turning off the run signal. Stop the motor, I really should say, not really turning the drive off. And then our motor at rest bit that I'm pointing at right now with my pointer just turned on. That means the motor just got to rest. Okay, so that is our demonstration of our hybrid setup where we're using primarily I/O to control the drive, but we're also using Modbus RTU for diagnostic purposes. Okay, that does it for our topic for today. Don't forget to sign up for training. We've got 2 courses available in the 4th quarter, Basic and Advanced. Get to our website and sign up today. All right, lots of opportunity to check us out in the field, in the Midwest and in the South specifically. Now, you'll also not only have a chance to talk to Horner personnel and some of our great channel partners, reps and distributors, but you'll be able to see some of these new products in action. So don't miss the opportunity. We'd love to see you out in the field. There are also plenty of opportunities to interact with Horner online if you don't want to leave your office. So you can check out our website, you can go to our YouTube channel, and you can also connect with us on LinkedIn. All right, so next week, we're sticking with the CPU summer, and we're going to talk about how the micro CPU250 works really well in an Ethernet IP environment. So yet another way you can use the CPU250. So don't miss that particular topic. If you haven't subscribed to our channel yet, don't hesitate to do so. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live and every time we post a new video. Now, before I close here, I do want to give a couple of thank yous. Thank you to Andy Cluck, who loaned me his CT demo. Much appreciation, Andy. I've used it on 2 different videos, so I tried to make good use of it. And then finally, some thanks to my buddy Jim Hausch, another great PowerMation sales guy, who gave me a few pointers to give me a head start on working with the CT drive. So it just saved me some time. So thanks again to Jim and Andy for all their help. So until next week, let's get out there and do some good.